Greetings once again to our last discussion of this third unit in our college algebra course. Right now we're going to take a look at how to solve exponential and logarithmic functions, and we'll look at a couple applications at the end. We will put together all of the skills that we've learned so far in this unit, and we'll add one more, and that is our change of base formula here that just says log base b of u equals log base a of u over log base a of b. So what that's saying is that if we need to, we can change to a log that we're more comfortable with, or a log that we can calculate easier. You know, the calculators only have buttons for common log and the natural log, and so we will take advantage of our change of base formula here to be able to work out the value of some of these expressions. I'll let you guys kind of read through the proof, and certainly if you have questions on that, bring it along. We pointed this out before. Make sure log base a of u divided by log base a of b, we can't just make that one log base a and then write u over b. So make sure that we know the difference there. Same thing with the logs, the quotient of the two logs here. That is not the log of the difference. Alright, and so I'll make sure that I hammer that home as we go forward as well. Alright, well, it says let's solve this particular equation, 4 to the x, using two different approaches. And so the first thing we'll do here is we'll take the log of both sides. After all, you know that corny saying that I've been saying the last couple lessons, if a cat's in the tree, you need to get a cat out of a tree, call the fire department. If you need to get an exponent out of the variable, call a logarithm. So I'm going to take the log of both sides. Log of 4 to the x equal log of 7. And then we know that from our last lesson we can push this exponent down, make it the coefficient. Log x times log of 4 equals the log of 7. And so x equals the log of 7 over the log of 4. Now another way that we can take a look at that, we know that we've got 4 to the x equals 7. Well, that's exponential. We know that we can rewrite this as log base 4 of 7 equal x. And then we can use the change of base formula, common log of 7 over the common log of 4, or, believe it or not, we could actually write the natural log of 7 over the natural log of 4. Those would give me my solution for x. And you say, well, those look different. Well, they may look different, but in fact they give us the same value. And the reason for that is when we look back up at our change of base formula, it says here if u is greater than 0, and of course our base here is 4, so it is, then log base b of u equals log base a of u, log base a of b. And all we need is for a and b to be positive real numbers and different from 1. And certainly with the common log we have a base 10, the natural log we have a base e. Now here it says use the change of base formula to estimate log of 7, or log base 7 of 13. Well, I can rewrite this as log of 13 over the log of 7. And I apologize, I forgot to open up my calculator, but we can do that here real quick. And we can type in that. Here we go. Alright, let's get off the main screen here. We can type in the natural log of 13 divided by the natural log of 4. Or we can type in the common log of 13 divided by the common log of 4. Whoops. There we go. Common log of 4. And we'll see, just as advertised, we get the same value. So it doesn't really matter which direction we go there. I'll let you guys use the change of base formula to estimate log base 3 of 6, and we'll take it from there. Alright, so let's solve some exponential equations, shall we? Said it 100 times. We've got a variable in the exponent. Let's bring in a logarithm. So log of 2 to the negative x squared equal log of 5. And so now we get negative x squared. I can pull that out front. Log of 2 equal log of 5. negative x squared equals the log of 5 over the log of 2. And so now the next thing that we're going to do is we're going to multiply both sides by negative 1, so x squared equals the opposite of the log of 5 divided by log of 2. Now if you look at this, you might notice that we may have a problem here because it says x squared is equal to something negative. Can you square anything and get a negative result? No, you can't, so we have no solution to this particular equation. Let's come in here with example 4. I'm going to take the natural log of both sides here, so the natural log of 3 to the 2 minus 3x equals the natural log of 4 to the 2x plus 1. So we've got 2 minus 3x times the natural log of 3 equals 2x plus 1 times the natural log of 4. Alright, well, we're going to distribute through here. Our goal is going to be to get x by itself, so we've got 2 times the natural log of 3 minus 3x times the natural log of 3 equals 2x times the natural log of 4 plus the natural log of 4. And so now we need to get all of our x's on one side, so let's see here, 2x natural log 4 plus 3x natural log 3, and over here I've got 2 natural log 3 minus natural log 4. Alright, and so the next thing we need to do is factor an x out over here. X times the quantity 2 natural log 4 plus 3 natural log 3. And we've got 2 natural log 3 minus natural log 4. And so x is equal to 2 times the natural log of 3 minus the natural log of 4 over 2 times the natural log of 4 plus 3 times the natural log of 3. And there we go. Now we can type that into a calculator. I'll let you guys play around with that, and if you have some difficulty, let me know. But this works out to be approximately 0.1336. Alright, so be careful. I may on the test ask for an exact solution, and I guess I asked for a 2 decimal approximation here, the solution, didn't I? So let's just go ahead and fix that real quick here. We'll make that a 2 decimal. There we are. So this is going to be 0.13 is what x is approximately equal to. So of course if you have questions, write those down, and we will take a look at those in class. This might be a good time to review a couple facts that we talked about in yesterday's lesson. If we have log base b of x plus log base b of y, we know this is log base b of xy. And if we've got log base b of x minus log base b of y, we've got the log base b of x over y. I've already used the fact that a logarithm will allow you to bring an exponent down and turn that into a coefficient. So we've got the difference of logs here. Now we know that the difference of the logs is the log of the quotient. Alright, and this equals the log of 1 over x. Now remember that if we've got the log of a equal to the log of b, then it must be the case that x minus 4 over 3x minus 10 equals 1 over x. So in other words, log of a equal log of b. A must equal b. And now we can do what I don't like my beginning algebra students to do. We can cross multiply here. X squared minus 4x equals 3x minus 10. X squared minus 7x plus 10 equals 0. Of course this will factor into x minus 5 times x minus 2. And so x equals 5 and x equals 2. Now, as I mentioned before, we have to check and make sure that we don't take the log of a negative number. If x is 5, 5 minus 4 is 1, we're good there. If x is 5, 3 times 5, 15 minus 10, we're good, and we're good. If x is 2, 2 minus 4 is negative 2, so we'll have to throw that out. X equal 5 is our only solution there. And so take a look at that for a minute, and we'll move on to our next example here. Now, this one may seem a little strange. You're thinking, what do we do here? Well, we've got this negative exponent, and negative exponents often are not good things. So let's get rid of the negative exponent. This is 3 times 3 to the x plus 9 over 3 to the x, and this equals 28. Alright, so again, you've got a negative exponent, push it to the other side of the fraction bar, that changes the sign on the exponent. Now what I'm going to do here, guys, is I'm going to clear the fraction. So this is 3 times 3 to the x times 3 to the x plus 9 equal 28 times 3 to the x. So in other words, what I'm doing, I'm clearing the fraction. Now we know that 3 to the x times 3 to the x gives me 3 times 3 to the x squared plus 9 minus 28 3 to the x. And you might remember in our first unit we looked at equations that were quadratic in something other than x. This happens to be quadratic in 3 to the x. Notice I'm going to let u equal 3 to the x here. And so this becomes 3u squared minus 28u, I'm going to flip-flop the order here, plus 9, this equals 0. And so now you look at this and realize that, hey, I can factor this. 3u minus 1 times u minus 9, this equals 0. So 3u minus 1 equals 0, u minus 9 equals 0, u equals 1/3, u equals 9, but remember, we're not solving for u, we're solving for 3 to the x. 3 to the x equals 1/3, 3 to the x equals 9, so here x is negative 1, and here x is 2. And so it is possible to deal with quadratics here, even in exponentials. And so we give you a few exponential equations to work for discussion, and then again for homework. And now we get into our log equations. This might be a good time to remind ourselves that if we have log base b of x equal y, we know that this means that b to the y equals x. So we take a look at what we've got here. My base is 10, so I've got 10 to the second equals the square root of x cubed minus 9. Now we know that 10 to the second, of course, is 100, and this equals the square root of x cubed minus 9. Now we're going to square both sides, so 10,000 equals x cubed minus 9, and then 10,009 equals x cubed. That means x is simply going to be the cube root of 10,009. Now we're looking at example 8 here, and you're saying, whoa, what's going on here? We've got the log base 4 of x plus log base 8 of x. All this equals 1. How are we going to go about handling this? Well, glad you asked. Different bases change a base formula to the rescue. We're going to rewrite this as the log, natural log of x over the natural log of 4 plus the natural log of x over the natural log of 8. This equals 1. And so now we notice that we can rewrite this as the natural log of x. Notice the natural log of 4 is the natural log of 2 squared, while the natural log of 8 is the natural log of 2 cubed. That equals 1. Alright, our next move here, we're going to move the exponents out front. Natural log of x over 2 natural log 2 plus the natural log of x over 3 natural log 2. So this equals 1. Alright, and now you're saying, well, where are we going now? Well, if I were to multiply everywhere, and allow me to change colors here for a minute, if I were to multiply everywhere by 6 log 2, then I think what we will find, 6 over 2 is 3 log x, the log 2's cancel. 6 over 3 is 2 log x, the log 2's cancel, and this equals 6 log 2. And so 3 log x plus 2 log x gives me 5 log x equals 6 log 2. And so the natural log of x equals 6 log 2 over 5. And now, of course, we've got a coefficient here of 6/5, so we can rewrite this as log x equals the log of 2 raised to the 6/5. And of course, if we are going to solve this for x, e to this power equals x, so x equals e to the natural log of 2 to the 6/5. Of course, e to the natural log, those are inverses, so 2 to the 6/5 becomes our final answer here. We know that 2 to the 6th is 64, and we need the 5th root of 64, so we can look at it that way if we want to. So take a little bit of time to digest that, and that one may take you a bit, so if you've got questions, you guys know the drill. Don't be afraid to write them down, make a note of them right now while you're thinking about them, and then when we're going over them in class, ask me about them. Let's take a look at example 9 here. And of course, anytime we've got a fraction, I've told you we want to clear that fraction out. So we're going to multiply both sides by 10 to the x minus 10 to the negative x. And that'll give me y times 10 to the x minus 10 to the negative x equal 10 to the x plus 10 to the negative x. Okay, so now, of course, we're working on getting all the x's by themselves. We're going to need to multiply through first here. It looks like y times 10 to the x minus y 10 to the negative x equals 10 to the x plus 10 to the negative x. Now, we could rewrite this as y over 10 to the x. If we wanted to, we could rewrite that there. But instead, we're going to just multiply everywhere by 10 to the x. And in doing that, that's going to give me y times 10 to the 2x minus y, because 10 to the x times 10 to the negative x is 10 to the 0, which is 1. And this is going to equal 10 to the 2x. 10 to the negative x times 10 to the x is just going to be 10 to the 0, which is 1. Alright, so we're going to need to get all of our terms with an x in them on one side here. So let's see. Y times 10 to the 2x minus 10 to the 2x equals y plus 1. And now I'm going to need to factor out that 10 to the 2x. So I've got y minus 1 here. This equals y plus 1. And so we've got we've got 10 to the 2x equals y plus 1 over y minus 1. And now, of course, we've got a base 10, so we can take the common log of both sides here. common log of 10 to the 2x equals the common log of y plus 1 over y minus 1. And so we've got 2x equal the log of y plus 1 over y minus 1. Multiply both sides by a half, so x equals 1/2 times the common log of y plus 1 over y minus 1. So we've worked some exponential equations, we've worked some log equations. Let's work some applications here. Alright, and boy, here's our compound interest formula again. And we're getting a lot of mileage out of this. That's okay. And so if we take a look here at this example, it says solve this equation for t using natural logarithms. Well, first thing I'm going to do is I'm going to divide both sides by p, so a over p equals the quantity 1 plus r over n raised to the nt. And now I'm going to need to take the natural log of both sides. The natural log of a over p equals the natural log of 1 plus r over n to the nt. And that will allow me now to push this exponent out front. So I've got the natural log of a over p equal nt times the natural log of 1 plus r over n. And now to solve for t, guys, this is just a matter of taking the natural log of a over p and dividing it by n times the natural log of 1 plus r over n. Finally, we look at our last example here, and we're looking at employee productivity. Manufacturers sometimes use empirically based formulas to predict the time required to produce the nth item on an assembly line for an integer n. If t of n denotes the time required to assemble the nth item, and t sub 1 denotes the time required for the first or the prototype item, then typically t of n, the time required to produce the nth item, is equal to the time required to produce the first item times n to the negative k for some positive constant k. Now it says here that for many airplanes the time required to assemble the second airplane, t of 2, is equal to 80% of the time required for that first airplane. And so they want us to find the value of k. Well, now here's what we know, folks. We know that t of 2 by the formula up here is equal to t of 1 n to the negative k. Now what is k? Well, k is what we're looking for. But we're also told here in part A that the time for the second one is 80% the time for the first one. Okay, so we've got these two expressions set equal to each other. Now it's a matter of solving for k. Of course, our t1s will cancel, t sub 1s will cancel. N to the negative k equals 0.8. And we need that exponent out, or we need that variable out of the exponent. So I'm going to take the log of n to the negative k equals the log of 0.8. And so now I pull the negative k out front. Log of n equals the log of 0.8. And so now we can and you know what, I just noticed we're looking for 2 here, so I can go ahead and plug in the value of 2 for n. My mistake. Make it easier here. So negative k equals the log of 8/10 divided by the log of 2. And of course k then will equal the opposite of the log of 8/10 divided by the log of 2, which that turns out to be 0.32. And so now we know what K is. K is approximately 0.32. Or another way that we can write this, remember that it calls for the time of to assemble the fourth airplane here. So T of 4 equals the time to produce the first one times 4 to the negative K here. But we might note that 4 is 2 squared to the negative K. And so this gives me the time for the first one multiplied by 2 to the negative K squared. And well, we know what negative K is here. K is just equal to log base 2 of 0.8. So we've got T1 times 2 log base 2 of 0.8, and we're going to square that. And so of course when we simplify that, 2 to the log base 2 just becomes 0.8, and we've got to square that, and so this gives me 0.64 T1. Okay, and then part C, they want us to find the time required to produce the 2nth airplane, and so here T of 2n equals T sub 1, 2n to the negative K, and so we know what we have here. We've got 2 to the negative K, and then what we're left with is T sub 1 n to the negative K. Well, we've been down this road before. We know that this works out to be 2 raised to the log base 2 of 0.8 times T of n, and so this gives me 8/10 of the time it takes to produce the nth airplane. And guys, that brings us to the end of this unit. If you have questions on anything, don't forget to bring those and ask them, and we'll be happy to go over them.